Hello everyone, it's Mr. Grant here, and today I wanted to do a quick review of equilibrium expressions. When you start learning about reversible reactions, one of the first confusing topics to arise will be all of these different K expressions. There's literally Ka, Kb, Kc, and so on. But why are there so many, and how do we use them? Reversible reactions are reactions that never end. As the reactants proceed to make products, so also do the products react to form reactants, creating an endless cycle that never ends. But it does reach a steady, unchanging state that we call equilibrium. This occurs when the forward and reverse reactions occur at the same rate, meaning everything is consumed at the same rate at which it's produced. We can predict how much of each substance will be present at equilibrium using an equilibrium expression, which is simply a ratio of the amount of products present at equilibrium to the amount of reactants. This ratio is called KEQ, the equilibrium constant, and is different for each type of reaction. Typically, the amounts in these expressions are shown as concentrations. When concentrations are used, we call the equilibrium constant Kc. For gases, sometimes it's more convenient to measure the amounts in terms of partial pressures. If using partial pressures, we call the equilibrium Kp. Ka and Kb are reserved for equilibrium expressions involving acids and bases respectively. I'll circle back to those in a later video. To find the equilibrium expression of a reaction, we write the products in the numerator and place the reactants in the denominator. If any substance has a coefficient in the reaction equation, we place that as an exponent on the substance's concentration or pressure. Kp can be used if the reaction involves only gases, while Kc can be used in any situation. It is important to note that in equilibrium expressions, solids and pure liquids are omitted as they do not affect the equilibrium concentrations of other substances. Pure liquids, though, they're pretty uncommon because we're usually mixing things together during reactions, but you should be on the lookout for solids when doing equilibrium problems, and be sure to omit them from your expression. So let's look at a classic example, the production of ammonia, NH3, from nitrogen and hydrogen. This is a gaseous reaction, so we'll write a Kp expression. In the numerator, we'll include the partial pressure of the product, NH3, and we'll square it because it has a coefficient of 2. In the denominator, we'll include our two reactants, N2 and H2, the partial pressure of each. We'll make sure that we cube the partial pressure of hydrogen because of its coefficient of 3. Okay, so here's our Kp expression for the production of ammonia. Here's another example. This is called heterogeneous equilibria because it involves substances in different phases. Notably, it includes solids, which we'll omit from our Kc expression. In the numerator, we'll just include that copper 2 plus and omit the solid silver that forms. Likewise, in the denominator, we'll only include the silver plus ions and omit the copper atoms. Remember, we need to square the silver ions because there's a coefficient of 2 in front of it in the reaction side of the equation. All right, that's it for our intro to equilibrium constants. Next time we'll look at Ka and Kb expressions, which are similar, but they have their own little oddities to them. If you have any questions, please let me know in the comments below. Thank you.